This is eHobbyist blog, a log of electronics hobbyist activities aimed at city dwellers who have limited space, limited money, and limited time. My name is Neil. Welcome. During this video, we will start work on the transformer secondaries and their associated rectifiers and filter capacitors. There are three transformers that will be used in the external power supply. All of them are toroidal transformers, and a standard shell-type transformer that will be used to power internal stuff for the prototyping system. The first transformer has a dual secondaries, each at 12 volts at 1.04 amps, and what I intend to do is to connect them in series such that the total voltage will be 24 volts at 1.04 amps, and that will be powering the 0 to 20 volt external supply. The second transformer has two secondaries, each one at 24 volts and 0.52 amps. When connected in series, I can use a connection point as a common and use either end to feed the 20 to common to minus 20 power supply. The third transformer for external power also has two secondaries. These are at 9 volts and 1.37 amps. If I connect these in parallel, what I'll have is 9 volts at 2.74 amps, and that is more than sufficient, I think, to power the plus 5 volt and plus 3.3 volt external power supplies. The last transformer is a packaged standard transformer. It is designed to provide 280 milliamps at plus 15 volts and minus 15 volts using packaged regulators, which is what I intend to do. The second secondary is designed to provide 2.8 amps into a regulator designed to output 5 volts. In order to specify components connected to the secondaries, I need to take a look at some critical parameters, and I'm just going to do this for the first secondary to give you some sense of what is going on in my so-called mind, bearing in mind that I'm not a professional electrician, and I'm sure that professionals would have a much clearer idea of what to take a look at and what formulas to use and so forth. But when I'm looking at, according to the manufacturer, a 24-volt secondary, that's 24 volts RMS. Now, I'm interested in peak voltages. As I recall from high school physics, to convert RMS to peak, you multiply by the square root of 2 or something like that. I'm not sure exactly what the derivation is. I probably knew it at one point in time. I'm sure that a professional electrician would know it. 24 times the square root of 2 works out to about 33.9 volts. And that is the peak voltage for the first secondary. Now, there's also a derating factor. It's a factor that is designed to deal with the demon Murphy. The demon Murphy is the demon that most affects hobbyists, and the demon Murphy says if anything can go wrong, it will go wrong. I need to reduce the number of things that can go wrong. One of the things that can go wrong is using components that are close to specification and discovering that you're not quite holding what you think you're holding. Yeah, I'm sure that 99.99% of the diode bridges specified at 1 amp will handle 1 amp. But I don't know for a fact that I don't have that 0.1% of a diode bridge that's going to turn into a massive blob of silicon the first time I use it. So I use a derating factor of 1.25 to get higher than the specs that I need. So, taking my 33.9 blah blah blah, I'm going to multiply that by 1.25, and I get 42.4 volts. That represents the minimum volts that my diode bridges and capacitors need to be able to deal with. Now, the bridges that I'm going to be using here for this particular secondary can handle 100 volts, which is fine. The capacitor can handle 50 volts, which is also fine. Now take a look at the current. Now, my specification for the current coming out of this first secondary was 500 milliamps. I didn't think I would need any more than that. But I look at the manufacturer's specification, and The manufacturer says that this particular secondary can handle 1.04 amps. If I want to be able to deal with that, I have got to design around a maximum of 1.04 amps for the diode bridge. Peak amps would be square root of 2 times 1.04, 1.47 amps. And if I put my derating factor of 1.25 into the mix, I get 176. So I need a diode bridge that can handle at least 1.77 amps. As for the capacitors, I'm going to be using 2200 microfarad capacitors for the 0 to 20 volts and 0 to minus 20 volt power supplies. And for the digital power supplies, I'm going to be using a larger 10,000 microfarad. The derating factor here is the same. You could derate electrolytics higher. Electrolytics have always given me problems. They're the first things to blow up, and maybe instead of 50 volts, I should be using 75. The problem, however, is if the derating factor is too high, you're throwing away money and volume. The higher the voltage for electrolytic capacitors, the more expensive they are, and the more space they take up, the more volume they take up. And so I have a completed circuit diagram for the rectifiers and filter capacitors. Now that I have that, next step is how am I going to implement that physically? I have chosen to use strip board on phenolic resin because I don't have problems with high frequencies or leakage currents, and I don't need to use the more expensive and more difficult to work epoxy fiberglass. Pattern of 0.15 inch just happens to be the spacing for a lot of my diode bridges, not all of them, and it also is almost sufficient spacing for the electrolytic capacitors designed by metrics fanatics. What I do next is to create a layout on top of the strip board design to show how components are going to be connecting to the strips. Okay, taking a look at the first transformer, the two secondaries connected in series. The ends of those secondaries going to get connected to the middle leads of the rectifier as drawn on top. And it seems to be fairly standard. The middle leads are AC. And one side is positive and the other side negative. Positive, the diode bridge is then connected to a strip that goes down to the positive lead for the capacitor. The negative strip of the bridge goes down to the negative lead of the capacitor. The capacitors are metrically spaced and don't quite line up, but they can probably be kind of bent into shape and probably going to have to drill a hole for these anyway because the leads are too thick. But close enough. As long as when I solder them, I don't solder bridge into the AC lines, everything is fine. Next, we're going to take a look at the second transformer, which will feed a dual plus 20 to common to minus 20 power supply. We have the diode bridge for that, and two capacitors, one on each side. The middle of the diode bridge is AC, as it was in the first one. The ends are positive and negative. The negative lead of the bridge goes to the negative lead of one of the capacitors. The positive lead of the diode bridge doesn't apparently go anywhere because I can't get or don't want to get the second capacitor on the left any closer. So I stuck in some jumpers. Notice that the first jumper on top goes from the strip carrying the diode bridge positive to the positive lead of the capacitor on the left. The negative lead of that capacitor gets connected to the positive lead of the capacitor in the middle, and that's going to be the common. That strip over the positive lead of the capacitor in the middle is going to go to common, and now we have a positive capacitor, common, and the negative on the capacitor. That is going to be used to power the dual power supply. Next, we put in diode and capacitor for the external digital supply. And here again, we have AC leads in the middle and positive and negative on the sides, but this time the spacing is not 0.15. It's probably 0.20, but by angling it such that the outer leads are connecting to perforations on the outer strips, the middle ones also coincide to the perforations. Looks like a 45-degree angle, and somehow the geometry seems to work out. This is not uncommon, where you have something that's larger than the spacing between strips. Put it off on an angle and see what happens. Anyway, the positive lead on the bridge goes to the positive of the capacitor. The negative lead on the diode bridge goes to the negative of the capacitor. In this particular case, so far, I needed 2 jumpers, but I didn't need to cut any of the strips, which means I can connect on either side, which is an advantage. Now we need to drill mounting holes, and the mounting holes are approximately ½ an inch from the outer edges, which is something I like to work with. Now I had labels on the circuit diagram, and I'm going to put labels on this drawing just to prevent confusion and to indicate how things are going to get connected. And so we have the perf board with labels. The next step in this is to create a diagram without the strips, looking from the top down. And that's what I have here. I have the perf board diagram of the components on the unclad side of the board looking down. What I'm going to do is print that off on a laser printer on transparency film. The toner's on the bottom. And now I can transfer that laser printer toner to the top of the perf board and use the laser printer to label the top of the perf board. In this video, I worked up a circuit diagram of the transformer secondaries, rectifiers, and filter capacitors. I specified components based on peak values and a derating factor. I chose phenolic FR2 strip board on a 0.15-inch grid as a construction medium and created a layout diagram for it. I printed the layout diagram on transparency film to be used to transfer labels to the strip board. In the next video, we will be fabricating the rectifier filter modules. If you like this video and the idea of the channel, click on the YouTube thumbs up icon. If you want to be notified as to when the next video is available, click on the YouTube subscribe button. If you want to suggest future directions or topics, make corrections to published videos, or voice your opinion on related matters, then leave a YouTube comment. If you want to see supplementary material that cannot be easily presented in video form, such as high-res graphics, files in different formats, lists of references, go to the corresponding website. Until the next time, good day.